All right, so did you look over the lab?
Yes.
Did any of you do any of them? Lena, you did, of course, because you're just
Yeah, I just did the first part with scientific notation, and then like the troughs and ridges and that
okay.
stuff.
So what I'm gonna do for this is, when you read over it, did you see anything that you may not be able to do? So what I'm gonna have you do, this is the way that I want you to do. I'm gonna make you do the lab independently and submit it before class on Thursday. Okay, so you're gonna do the lab before class on Thursday, and you're gonna submit it, and I'm gonna take a look at it. After we go through it, you will probably have an opportunity to resubmit it, and then we'll make sure that it's right. So I want to see what you can do independently by reading through the lab and working on it. We've already done a lot of these things. The key things about that, so if you could take a look at the lab, is it deals with prefixes, and I give you explicit example of how to solve problems. And that's super important that you do that in the steps that I do. So I want to see what you do first. We'll go through some stuff, then you can make adjustments to it, and then I'll grade it. But you have to turn it in before Thursday. Is everybody good on that? Does everybody understand what I'm saying?
Mm-hmm.
Yeah.
Problems getting it done? Okay, so I want to talk about more important things, and that is getting into Blackbody. Because some of the radiation stuff we've already done, we've already kind of alluded to a lot of things. So most of the radiation stuff is easy, except for the Blackbody stuff, which is some really cool things. So I want to get into the science of this all. Before we do that, let me share my screen. And this is an intro to meteorology class, right? So we do weather sometimes. We actually talk about the weather. So did you guys, I mean, Sam, I know you did, but did you guys see tomorrow?
Wicked scary. Very, very scary tomorrow.
Right, so we have a big area. It's already what we call, this is the area of tornado potential. And in common words, it's a moderate risk of severe weather across this area.
They actually mentioned
Risk.
that
Yeah.
they might actually upgrade to a high by day one.
So at the end of this, it says, thunderstorm development also be possible late tonight. Wait, no.
That's today's.
Oh, that's today. So yeah, I'm looking for day 2. Thank you very much. So let me go through this thing. First of all, whenever you see this word, that's serious. And there's a moderate risk that usually is where they start to use the word outbreak of severe storms, is capable of producing large hail, very large hail, intense damaging wind gusts, and more than one round of severe storms. And some of them will be producing tornadoes. Some of them may be intense. So on the tornado spectrum, do you know what the tornado spectrum is called? What's the scale that measures tornado strength? What's it called? Go ahead. Lena, you remember?
Yeah, is it the Fujita or the enhanced Fujita?
Yeah, the enhanced Fujita scale, which is basically FUJITA. This is a damage scale. It goes from EF0 to EF5. And these are called weak tornadoes, and these are called strong. Strong tornadoes get really damaging, and then these last ones are called violent. And so there are the risks for some violent tornadoes tomorrow. That's a possibility. But if we look over here, I just want to kind of talk about a couple words that we can find in here. So in order to get storms, I require lift, moisture, and instability. Now we've already talked about this and this. Lift might be from fronts or something along those lines. And then to get severe, then I need vertical wind shear, which we've talked about also. So vertical wind shear, which is dV dz.
That's the question.
That's a question. How does the wind change with as you go higher? Okay, so when I look over here, it says there'll be a surface low pressure. This is unit 4 stuff. So low pressure means air is converging and going to be forced to rise. So this is a lift. We have a warm front, and then there will be a cold front coming in later on. We have dew points in the mid to upper 60s. So we talked about how important dew points are. We have steep lapse rates. That's the environment's cooling. So that gives me more CAPE. We have intense vertical shear. That's really strong tomorrow. Capable of supporting a widespread severe weather outbreak. It says convection will be ongoing. So convection refers to thunderstorms, CBs, cumulonimbus, will be ongoing Wednesday morning near the surface low and along the cold front. That's the lift. We talked about some elevated storms for large hail. Shear profiles will improve through the morning, and surface-based storms near the triple point and along the warm front are possible. Increase the risks of damaging wind gusts and a few tornadoes. Further south along the cold front, convection will move into an increasingly unstable and moist environment. A line of supercells, storms with rotation. So the updraft is not only strong, it's also rotating, and that's what calls a supercell. All severe hazards are expected. I'm not going to get into this now, but we have a second round of severe storms capable of intense tornadoes. This is true overnight from 7 to 10 p.m. So an upgrade to a high risk. Now, high risks are only issued maybe 2 or 3 times a year on average. Sometimes we get no high risks a year. Sometimes we might get a few more. But the fact that tomorrow looks like it's going to be a high risk of storms is a pretty significant, and it's a pretty large area. I mean, when you look at this region of the moderate risk, that's parts of Arkansas, Louisiana, Tennessee, Mississippi, Alabama, maybe even into Georgia. That's the area that I'm really concerned about. So that should be pretty interesting to watch tomorrow. But we've dealt with a lot of the storms. So let me show you a couple of things on a model. Okay, so the first thing that we're, oh wait, you know what I need? Nah. Oh, this is fine. What I can do is I can show you CAPE. So I'll look at CAPE on here, and you'll see that tomorrow there's a large area where the CAPE is over 1,000 to maybe 2,000 joules per kilogram. So this whole area in blue to green is pretty intense. The wind barb is not the actual wind speed, that's the difference in the wind, that's wind shear. And if I'm up over 40 to 50 knots, that's a lot of shear. And here we're looking at 65, 70 knots of shear. So if I were to look at a sounding from over here, I am unable to
Wait,
just,
so those wind barbs with the Meanler Cape, so that's just saying those,
this is the difference, Sam, between the surface winds and 500 millibars. It's just the difference between those two vectors. And
okay,
so it approximates just the deep shear.
so the direction doesn't matter.
It just means that the storm should be moving in that direction.
Okay,
That's pretty close to what it's going to be.
that makes a lot of sense. Thank you.
Now, why I can't get a sounding to load, I'm not sure why.
Try in the highest Cape area.
No, I'm not getting a sounding to load. We're having problems getting soundings loading.
Weird,
So
I was able to pull them up.
when did you pull them up last? You know, it might be because I'm not on, here, let me do this. Let's try it. Let's try it here. It might be because I'm on a floater. Oh, there we go. So here's the winds. So this yellow line is basically your blue line. So let's just go here. There's your parcel. There's your wet adiabat all the way up. So there's your EL. There's your LFC is right near the ground. At the LFC and the EL is about the same. That's really impressive. The other thing that, Sam, that is very impressive is your 0 to 3 kilometer cape is probably pretty high. Yeah, 145. That's way impressive. So lots of instability. Capes are up over 2,000, something along those lines. Very moist atmosphere. Winds are strong. If you look at what the model is expecting, tornadoes.
There's quite a few PDS soundings tomorrow as well.
So these are all the things that we did in class. In fact, let me look at one more thing. I'll look at the SIGTOR. This is sort of putting all the information together about what makes significant severe weather. So let's look over here. This is probably going to be pretty impressive. And then over here it says PDS tornado. So when you see this PDS, PDS stands for particularly dangerous situation. That's a lot of helicity, 0 to 1, 370. This is a serious setup tomorrow evening for very deadly tornadoes. If this shows up to be true, we're probably talking about a number of death reports.
Tomorrow is one of those days where it's
Right.
You've got a feeling that storms are going to be turning deadly tomorrow. It's one of those days.
Yeah, you just have this, you have this whole area. This is what the radar would look like. This is what we call a forecast radar. Tomorrow we should see a number of storms forming. All these storms here are capable of producing tornadoes. So lots of storms, lots of supercells, lots of potential devastation. It's in rural areas where people don't necessarily live in well-built houses, a lot of prefab houses that are up on cement slabs. So there's no basements. It's happening maybe in the early evening hours. Tomorrow is it's a situation where bad things happen. Let me show you one more thing.
The one thing about tomorrow is that the low-level relapse rates are rather gross.
Here, this shows you where the populations are in the moderate risk, where there's big population centers. So Jackson, Mississippi, Little Rock, Memphis. This would be up in Birmingham, Alabama. So this is where a lot of people live. High cities. There's your cities.
Got almost 10 million people in that
There's your interstate.
moderate.
So it's, yeah, here's 10 million or 8.1 million people are in this region. And if you think there's going to be serious tornadoes, you know, you're going to get death and destruction tomorrow. So it's a really serious situation this time of year. It's the exact time. Let's look at something like we talked about the dew point. So let me show you.
Waking up.
Let me show you the dew point in this region. The blue is 60s. And when we get into tomorrow, there's dew points that are showing up in the 70s, 71 degree dew point, 68, 67. So all of these upper 60s is almost perfect setup for severe weather tomorrow. So you don't see high risks very often. We probably need to look at that. I may send out a message if anybody wants to talk about things tomorrow, we can. But it's going to be pretty interesting.
I
So
would like,
any questions, comments?
Isn't that like kind of south of Tornado Alley though? Are there usually like tornadoes in that region?
That's a great question. Let me show
Yeah.
you something about tornadoes. Actually, let me do this because Shannon, that's a really good question. And I'm going to show you a presentation I gave at Woodridge. When we look at tornadoes, first of all, here's where tornado tracks have been over about a 60-year period. And all the bright regions are some of the strongest tornadoes. So notice it's over Louisiana, Arkansas, Mississippi, Alabama. When we look at all tornadoes, I know that you probably think, well, isn't Tornado Alley this area here? And yes, that's definitely where abundance of tornadoes are. But when I start looking at the deadly tornadoes, notice it shifts over here. And when I look at significant, that would be EF2 to EF5, which are the strong and violent tornadoes. Look where it's maximized. So tomorrow is a perfect typical setup for March, and that's where the significant tornadoes, and that's where the deadly tornadoes are very, very common. So we call this Tornado Alley. You could even say Tornado Alley goes here through Illinois, but this area is a slang name we call Dixie Alley. And its worst is like March through early May. That's when it really gets hit in that region. So
if it's
not uncommon. In fact, it's extremely common for this time of year. Now, if it was June, I wouldn't expect that. I'd expect the Midwest. But over here, this is where it's going to be. And, you know, here's another thing, Shannon. Let me show you one more thing here. Notice that the next day, so today there's a risk in Oklahoma, Texas. It moves to the east. And then where does it end up on Thursday? In the southeast, in the Carolinas. So this whole system is moving west to east like we would expect. If I go into the future and I look at maybe an area of high instability, so same thing that we were looking at before with Cape. There's the area. Notice it pushes off the East Coast. And then next week, there's another little area that comes up, doesn't look as big until this date. So again, Cape and Shear exist over there.
when is that?
That would be next Thursday, Friday. So you'll probably repeat the whole setup next week. This doesn't look as bad in the middle, but you know, you get these outbreaks once or twice, maybe, you know, March into April, it's going to happen a lot. So it's a great question. And hopefully that provided the answer for you. Other questions, comments? Do you like severe weather? Are you into tornadoes, Tim? That's kind of cool. I'm into ginger ale. Okay, so let's move on to black bodies. Okay, so what is a black body? Now this, you should be going to your notes. So get out your notes from this section, and I'm just gonna, I can look at them here for Unit 3. So black body, what is a black body? So here's the definition of black body that you ought to know. And since it's written down, there it is. It's a hypothetical body. So question, boys and girls, why talk about something that's hypothetical? What do you think, Zach? Why talk about hypothetical objects? What does that mean?
It would give us like a better understanding about how it really works, because isn't that how like the parcel was a hypothetical parcel that helped us better understand how clouds
Okay.
function?
Why not talk about it in reality? Why talk about hypothetically?
Because we can control much more variables than in reality.
Okay, you see, that's really good. It controls things better. You see, we say that an object is a black body because it does certain things. And what we're going to say is we're going to do it perfectly. So in physics, have any of you taken physics before in high school or even college? Did you ever do frictionless surfaces? Okay, the reason you do a frictionless surface, all surfaces have friction, is because it's easier not to worry about friction all the time. So you can focus on what you want to focus on. So that's the way it's going to be with a black body. So, and we are going to assume that objects are black bodies. So the sun is a black body. The earth is considered a black body. And we'll talk about how it's not exactly. So what does a black body do? Well, first of all, it says it consists of a sufficient number of molecules. Now, here, do me a favor. If I were in class, I would throw something at you. So take something, throw it up in the air and catch it. True or false? You have a sufficient number of molecules that enabled you to catch the pen. Is that the way you would say it, really? Wouldn't that make everything kind of pointless? Just to say, well, how do you define a football? Well, it's a sufficient number of molecules shaped like a football. You know, that doesn't make sense. So why would I put that in this definition? What do you have a sufficient amount of to catch a pen? Coordination, hands. I have a sufficient, like if you didn't have any hands, it would be harder to catch a pen. So why say molecules? What do you think? Talk to me. Let's have more conversation today. I hate my voice. I don't hate my voice. I'm just tired of talking. What do you think, Lena? If you caught the pen, what caught the pen?
Well, my hand did, and
Right? So I'm assuming your hand's made of molecules, but it's your hand that did the action.
yeah.
So when we're talking about a black body, what's doing the action? And more importantly, what is the action?
It's whatever we define it as.
Well, look what it says in the definition that you have in front of you.
Molecules.
What's the action?
Absorbing and emitting electromagnetic radiation.
Okay, so it's the molecules that are doing the thing that we care about. And the thing that we care about is to absorb and emit electromagnetic radiation. So even though we say that the Earth is a black body, what we're really saying is that it's the molecules on the Earth that are doing the absorption and the emission. It's not the whole object. It is the molecules actually doing the work. So that there's sufficient number of molecules means that all of what needs to happen is able to happen. Well, what is supposed to happen? What does it say right after that? So that, what's the first numbering point?
All radiation is completely absorbed.
Okay, so all radiation, all what kind of radiation?
Just all of it, because it says all parts of the electromagnetic.
Oh, here, yeah, but look at this word that I've highlighted. What does that word mean? Do a web search on that word. Define it. What does that word mean? Anybody? Isaac, do you have it?
It's an event or an occurrence. But maybe I'm not looking at the right word.
I mean, I understand that, like an event, like there's been an incident in the parking lot.
The electromagnetic radiation that is being used to eject the electrons in the metal.
Okay, that might be a little bit too technical. Anybody else have an idea of what that means?
Yeah, I found one. It says, especially of light or other radiation falling on or striking something.
Okay, so anything that's falling on or striking an object. So in other words, anytime radiation hits an object, that's the incident radiation. And what happens to all of it? The answer is it's completely absorbed, which means what? What is true about a black body? Let's see who among you is the smartest. Or the one that's going to get the most wealth in life, or is the prettiest, or something like that. If all incident radiation is completely absorbed, what's true about a black body?
Not sure. Okay. It's not transparent at all.
It's not transparent. And what else? Erin, what does Erin have? Does she have something that she's? Because I'm looking for a very specific answer. It's an answer that all of you ought to get.
Is it that it's black?
Why do you say that, Ryan?
Because then it would absorb all light.
Okay,
Eric,
what kind of
it doesn't reflect.
It doesn't reflect, right? So if it absorbs all of it, it doesn't reflect anything. So why do you see color? Okay, see this pen? What color is this pen?
Purple.
Okay, it's purple. Lena, you're looking at like.
I forgot if it's blue or purple.
It's definitely purple. This is blue, right? See that little blue button there?
Oh yeah, that's definitely blue.
Okay, so why is something blue or why is it purple? Why do you see this as a color purple?
The wavelength.
Because what's it doing?
Isn't it like similar to how we view the sky? Like that the sky is blue because it's the only color that's like reflected back and all the other colors get absorbed?
No, do not, no. Boo, not boo. But I'm warning you, if you say what you said ever again, you're going to fail the test. So don't say that. Colors are not absorbed by the sky because what did we say the atmosphere was to light? Using the word that Tim just said.
Transparent.
It's transparent. So the colors are not absorbed. We'll talk about sky color later on. So let's ignore that for now. But why do you see this as purple? Because purple light's being reflected.
Mm.
And we're going to talk about the nature of light in a second. But so Erin said all of it's absorbed, or Ryan, you said all of it's absorbed. Erin, you said none of it's reflected. So what's a true statement about a black body? The word I'm looking for starts with an A. L.
Albedo.
What's the albedo?
100%.
No. What is albedo defined as? Albedo is defined as how much is reflected. So how much is reflected? Zero. So the albedo of a black body is 0. That's by definition. Now, Ryan, you brought up an interesting point. Is a black body black? if it's reflecting nothing. I'll give you a hint. The sun is a black body. Is the sun black?
No.
Why do you see it?
Oh, because it's reflecting,
No,
or it's emitting the light towards
it's
you.
emitting light. This pen is not emitting light. It is reflecting light. So now let's talk about the nature of light. So I'm going to pull up paint. Okay, so we can play with this for a second. Now, what is white light? What's white light? Do you know the three primary colors of light?
Blue, yellow, red.
No.
Blue, green, blue. Yeah. Red, green.
Red, green, and blue. Those are the three channels of light. You have a monitor. Your monitor is called an RGB. It's red, it's green, it's blue. And in your computer, each pixel, each information is colored from 0 to 255 of red, 0 to 255 of green, and 0 to 255 of blue. And given those three combinations, there's more than 16 million colors that you can generate with the computer. Now, let's talk about this for a second. So when I look at here, I'm going to say, let me edit the colors. And I look at black. Notice over here it says red, 0, green, 0, blue, 0. What is white? It's going to be 255 of all three of those colors. When I mix equal amounts of red, green, and blue, I get white. If I have no amount, I get blue. So if I go to 192, 190, 192, 192 of all three, then I get what?
Gray.
Gray. How many shades of gray are there?
253.
Well, no, it'd be 200. I suppose you could make the comment. You'd have 256, right? 0 to 255, that's 256. But if you said that one is black and one is pure white, then you have 254 shades of gray. Unless you follow that stupid book, then how many shades of gray is that? 30, 40 shades? What is it? Mina, what's the name of that stupid book?
I think it's 50.
50 shades of gray, whatever.
Yeah.
It's obviously it's not 50. There's 254 shades of gray. That's what the book should have been called. Now the question is, what if I have equal amounts of green and blue? Put those two together. What do I get? So I'll start with this. I'll go to green and blue, and then I'll take red, and I'll make red 0. And what do I get? Anybody know what color this is?
Cyan.
This is called cyan. That's cyan. And if I take equal amounts of blue and red, what does that make?
Purple.
Red, not purple.
Oh.
What color is that?
Magenta.
That's called magenta. And if I take equal amounts of red and green together, what do I get? Most people don't know this. What do you think I'm going to get? Yellow. So when I do something, I have red, green, blue, and then I have yellow, magenta, cyan. And so if you're doing printing, you have what's known as CMYK, cyan, magenta, yellow, and black. So if I'm printing, I need those 4 colors. These are the 4 toners, and those are the colors that you make up. So all of these colors, right? So which color do you want to look at? Which one's interesting? Let's look at this burnt red. 128, it's just darker red. What if I wanted orange? Well, then I have a lot of red, some green, and some blue. If I wanted something that looks like almost sky blue, maybe over here. So all these things get names, and they're all based on those RGB colors. Does that make sense to you guys? So when I see light, white light, I'm looking at an equal amount of all 3 colors. That's why a cloud reflects all colors equally, and I get white. Unless there's not that much light, and then I get gray. And if they're shadowed, they get darker gray. And then eventually it becomes almost black. Does that make sense to you guys? That's color wheel. This is called a color wheel over here. By the way, one other thing I just want to point out. Have you ever heard of sunglasses that are called blue blockers? What color are blue blockers?
They're like yellow.
Right? If I'm blocking blue, then I'm going to be shifted towards yellow. So your glasses are yellow because they're blocking blue. Think about the sun. What color is the sun if you were out in space? For the most part, it's white. But if I asked you to draw a picture of the sun, what color would you use? What color would children use?
Yellow.
Why is it yellow? Because blue light is being scattered out of the light of the sun, making up the color of the sky, and what's left is yellow. So when I take out blue, I have yellow. I'm taking out blue from the sky, and the sun has a cast that's definitely yellowish. In outer space, it's going to be white, much more white. Okay, does that make sense to you? It's kind of cool, isn't it? This is something you didn't think about. So when I'm looking at all this stuff, that's some ideas of color theory. So let me go ahead and close out of this and go back to my definition. Oops. That is a black body black? Well, a black body is black if it's not emitting anything. But what also happens is this. In all wavelength bands, in other words, all different types of wavelengths, all different names of radiation, and in all directions, and that's a word that says it's called isotropically. So this word isotropically means equally in all directions. You need to know that. Sam and Lena, we talked about this in terms of Doppler radar being an isotropic radiator, and then we have a dish that focuses it. And then the last 5 words of this thing are the ones you really need to put down. Maximum possible emission is realized. You need to highlight that because this part of it is what we need to understand. What does that mean, maximum possible emission? So what kind of radiation hits a black body? All kinds, doesn't matter what. And everything that hits it is completely absorbed, giving you an albedo of 0. And then it will emit radiation as well in all directions and in all different wavelength bands. But does the sun emit visible light? Is this a wavelength band? Say yes. Does the sun emit infrared radiation? Yes. Does the sun emit X-rays? Yes. Does the sun emit, what are the other bands called? Well, if you go back up a little bit, it says here's some of the other ones. X-rays, ultraviolet, infrared, visible, microwaves, and radio waves. And it's all based on the wavelength. So the wavelength, right? When we look at a wave, the wavelength is the length of one complete oscillation or one complete wave. That's the wavelength. By the way, this letter, what letter is this? What letter is this? Mary had a little
Lambda.
lambda. That's lambda. It's the upside down Y. And lambda stands for the wave length. Is that right? By the way, Tim, ILL.
I baby.
That was amazing weekend. Did you watch the games I take it?
I watched every single one. Yeah.
Dude, Illinois is a fun. They're my favorite team. They're fun to watch because they've got all different types of people. They got the big guy who's crazy big, and then there's shooters and Williams. Was it that's name Williams? Shooting.
Yeah.
Oh my gosh, just it's so fun to have every aspect.
12:15 on Friday. First game.
Against wait, who they playing?
Drexel.
Drexel. Not a problem. The next game will be the tough one.
Yeah. It'd be fun to play Loyola.
Yeah, I know. I just want to beat them all. Okay. Okay, so those are the wavelength bands. So it says over here that in all wavelength bands, maximum possible emission is realized. Okay, so what does that mean? What we need to draw here is, or think about this way, is do you think the sun gives off the same amount of visible light as it does ultraviolet radiation? Isaac, how do you answer that question that I'm asking here? If the sun is a black body, does it give off infrared radiation?
No.
Say yes. Look what it says. All wavelength bands. It's going to give off radiation in all wavelength bands. Is it going to give off infrared?
Yes.
Is it going to give off microwaves?
Yes.
Is it going to give off gamma rays?
Yes.
Okay. Do you think it's equally in all those?
Did you say equally in all of those?
Yeah. Do you think it'll give off the same amount of X-rays as it does visible light? Lena, you're shaking your head. What are you thinking right there?
I was looking at the notes, what we were just looking at, and maybe I'm wrong then, because I was looking at the electromagnetic spectrum, but I might be wrong on that, but maybe it is because it says that it's isotropically, which is equal in all directions. So I don't know if that really.
Well, it's giving it off equally in all directions, the way that it's being transmitted. But is it going to give off the same equal amount of all different types?
No.
Like we already know, does the sun give off as much ultraviolet as it does visible? We've already mentioned this. How much of the sun's light is ultraviolet?
Isn't it like 2% or 1%?
Well, it gives off 7%, but it only lets through 2%, right? Through the atmosphere. So that's where the 2% is. But only 7% is ultraviolet. So clearly it's not equal in all bands. So what am I trying to find out? It's like Monopoly. You guys have played Monopoly, I take it, sometime in your life?
all the time.
Okay. Do you give off, when you deal out the money at the beginning, do you give the same amount of money in each denomination?
Yeah.
Really?
Oh, I thought you meant to each person. No, like you get more of a smaller bill.
Right. So you know, like there's there's a 500 and then a couple of 100s and 520s or something like that, right? You give off more in different things. What are you doing to the money when you start a game? What's that called? What's the word? You're doing what to the money?
Distributing.
You're distributing the money, right? So we're talking about something called a distribution. Well, in radiation, we have something that's known as Planck's Blackbody distribution. That's what we're going to be talking about. We're going to distribute radiation into bands. Over here, we are going to draw it as a graph. Distributions are best on, well, you can do distributions different ways, but I'm going to do it on a graph. And this distribution is going to look something like this. Something along those lines. Sorry, it's not really perfect. Now, if I'm going to draw a graph, what's the first thing I really need to do?
Label it.
Okay, so what is this axis? This axis is going to be something we call E star. This axis is going to be the wavelength. Now, wavelength is in meters or micrometers or whatever. This E star, I think in your book may call it I. What does I stand for? I stand for nothing. What does I stand for? What does it say in your book? Do you see I in your book on this stuff? What chapter is this in? Everybody get your book out. What chapter is this, Lena?
I'm looking. It's
Chapter 4, maybe?
yeah, that's where it has heat and energy transfer.
Here, page 61.
So is I the energy emitted by Earth?
Well, it's energy emitted. You know, it could be by anything, right? But what does that mean? Do it. Tell you what, do a web search for Planck's blackbody distribution and tell me what you see there. It's not really that either. It's not symmetric. It's not a bell curve. What do you see? Do you see anything interesting in there? What does Wikipedia say?
I'm saying intensity.
Does anybody see this word? Or this word? What do you think, Zach? Look up those two terms. All of you, Shannon, look those up. And somebody look up insulation, somebody look up energy flux.
Energy flux is the rate of transfer of energy through a surface.
It's okay. Listen. So write down what Zach just said it was. Say it again so everyone can hear you.
Energy flux is the rate of transfer of energy through a surface.
It's the rate of energy transfer through a surface. Draw a picture of it. I'm going to see if you can understand what I mean by that. I'm going to look at something here. Hold on a second. I'm looking for a picture. Because I took a picture of something and I thought this is what it looks like. And I just have to see if I can find it. Oh, here it is. I found it. Can you see this? It's good. It's really reflective on the window here. That's better.
Is it a plant?
It's a thing. Yeah, it's a plant vase. I don't know what those things are. But to me, that's what I see. So it's a rate of energy transfer. Well, what do you call energy transfer? What do you call energy transfer? By the way, these are all things you know. This is not new to you. What do you call energy transfer?
The work?
No. Energy can do work, but what do you call energy transfer?
Aaron says warming.
Not warming. You're close.
Would it be like conduction and convection and stuff?
Isn't that just heating? So you're not thinking warming, Aaron. You should be thinking heating. Heating is the transfer of energy. Now, what are the three ways of transferring energy? Conduction, convection, radiation. So what kind of energy are we trying to visualize? In this example, radiation. Well, what does radiation look like? Wavelengths. So, but Zach, what did you say? It's through a what?
Through a surface.
Through a surface. So how do I draw a surface? What's the easiest surface to draw?
Just a molecule, like a single.
No, that doesn't look like a surface. What's the easiest surface to draw? Sam? Here, everybody turn on your mic. You're not talking to me. I don't like teaching without talking to somebody. What's the easiest surface to draw? Why? What are you thinking of when I ask that question? If you don't understand something, you need to respond to me.
Aaron says a plane.
Isn't that the easiest surface to draw? Just a plane? Not a plane like an airplane, but like a plane, right? So if I drew a plane, I would draw a plane. Right? Is that a plane? So what do you see coming out of this, through this surface? Radiation. Right? So you'd see waves coming out of the surface. And the amount of radiation that comes out of the surface is the energy flux, or what we call insolation. Insolation with an O, not a U. However, what kind of radiation is a black body distributing or giving off, emitting?
Isn't it every type?
Every type. And what determines the type of radiation is the what?
Wavelength.
Is the wavelength. So shouldn't some of the wavelengths be really small wavelengths? And some of them should be really long wavelengths? Right? All different size wavelengths. Isn't that what you should be visualizing? Flowing through the surface. That is an energy flux. Flow through an area. Now, let me show you that picture again. Isn't that what it looks like? Right. It's just a weird plant, but don't they all look like wavelengths and they're all different wavelengths? So that's how I picture energy flow of radiation through a surface. Now, when we're talking about a black body, what kind of a surface are we probably talking about in terms of like planets and suns and things? Wouldn't it just be a big sphere? So imagine that you have a big sphere, right? Here's a big sphere, and you're covering the sphere with little tiles of carpet. You know what a carpet tile looks like? A little square of carpet. You're covering the entire sphere with these little rectangles and little squares. Does that make sense to you? Yes or no? Hello? Yes or no?
Yes.
Okay. So radiation's coming from all of them going out. And so it's going to come out equally in all directions from the sphere. And they're all different types of wavelengths coming out of this thing, right? But it ends up going equally in all directions. That's what the sun is doing. That's isotropic. What is the unit of E star? Do you understand what a unit is? What's a unit? Sam, what's a unit?
Are you asking what the unit of E star is, or a
No,
unit?
I'm asking you, what is a unit? Write that down. Everybody, what is a unit? Did you write a question? Yes or no? Did you write it as a question? What is a unit? Question mark? Isaac? I didn't say question. I said, what is a unit? Period.
Okay.
Look. See this pen? This pen is 4. If I said that to you, Isaac, I said, this pen is 4, what would you say to me?
For what?
Wouldn't you say for what?
Yeah.
That's the unit. That you're looking for the unit. I gave you the number, but I could say 4 inches. Then you go, oh, that's the unit of length, right? What if I said 4 years old? That's a unit of age, isn't it?
Yeah.
I could say, what's 4 degrees Celsius? What is that a unit of?
Celsius or Fahrenheit temperature.
Temperature, right? So when I say it's 4, that's just a number. You'd say for what? What is the unit? So what is the unit of energy flux? This is giving off 18. 18 what? Zach?
Since we're talking about energy transfer, would it be like joules?
Okay, but you're not looking at energy transfer. What did you say it was exactly?
The rate of transfer of energy through a surface.
The rate of energy. Well, joules is definitely energy, right? We talked about Kate and 2,000 joules, but it's a rate of energy. What do you call a rate of energy? What do you call a rate of energy? You know this. What is it? That was a joke. Tim?
Would it be power?
Yeah, but the rate of energy is power, but what's the unit? You have light bulbs, don't you? What are those?
Oh, watts.
Watts.
Watts. A watt. Oops. So a watt, by the way, what's a watt? Is a joule per second. Do you agree that when it's divided by time, that makes it a rate? So it's a watt, but you called it what? Zach, you said it's a rate of energy transfer through a surface. How do you say what's in the box? How do you say that which is in the box? How do you say this? Somebody say it. Ryan?
Yeah, watt times meters to the negative second power.
Is there a better way to say this? Here. What is it? Isn't that true? That's how you use negative exponents, just the reciprocal. Like, tell me this, you get this.
Yeah.
So really, I'm saying this is, how would you say this?
Watts per meter squared.
Right. But since that's exactly the same thing as watts times meters to the minus second, that's how you say this, watts per meter squared. Okay, this is a better way of notating it and writing it than this. So really this would be joules s to the minus 1, joules per second. This is actually the standard way of scientific notation. You don't usually put it divided by. But when I say the amount of energy coming through a surface, words like through, into, per, those are all indicating division problems. Divided by. So when it said it's the energy transfer, energy, rate of energy, that's a watt, transfer through a surface per meter squared. That is the unit of, I'm sorry, you know what, I lied. Just so you know, I'm lying about this whole thing. This is not insulation. This is called irradiance. So I've been lying to you this whole time. It's called irradiance. So I can stand for irradiance, or E star stands for irradiance. It's an energy flux. I'm going to use E star. I think the book may talk about I, whatever. But that's what the left axis, the vertical axis, is going to be. Irradiance. So look this word up, irradiance, and tell me what it says online in a web search. What do
It
you have?
says it's the flux of radiant energy per unit squared.
Per
Unit area.
unit area squared, right? Per unit area, which is a meter squared. And it's a flux. Flux just means flow through an area. And it's the energy flow through an area. And the energy looks like radiation. And what kind of radiation is flowing through it? All types, according to this distribution. Now, let me do it this way. Get rid of some of these things. Well, it's a lot to erase them. Okay, so now we have this thing called irradiance, and we're all happy with that. And then the question is, this is the irradiance, this is the wavelength, but there's something different about this horizontal axis. This horizontal axis is two things. It is logarithmic. Okay, let's see how smart you guys are now. How many, raise your hand, have worked with logarithms in your life? Aaron, have you done logarithms? You've never done a logarithm?
You did a little in high school.
In high school. Shannon, how about you and Tim?
Yeah, I did once or twice in high school.
Okay, so you've all seen them sometime in your life. What is a logarithm?
What was the last time?
No, just what is it? You've all dealt with this. These are the kind of things that drive me crazy about your high school education. Because you've had this stuff, but you have no idea what it is. So why did you waste time doing it? You did it so that you could do it, and you're like, I don't even know what this is. So we need to understand what logarithms are in simple terms. Does anybody know?
Isn't it like a certain quantity, like representing a fixed number, which is the base, which must be raised to a certain number?
You're not wrong, Shannon.
Okay.
You're not wrong, right? But what is it? I mean, I want simple terms, simple things that if you were truly educated, you'd go, oh, I know what logarithms are. They do this. What's the purpose of it?
You know, they deal with exponents and like converting exponents.
Okay, it has something to do with exponents. Now, what do you call something that grows with exponents?
Exponential.
Exponential. Okay. So imagine something exponential is going to look like this. That's a different type of curve than this. What do you call this?
Linear.
Linear. So what happens is a logarithm takes something that's exponential and makes it linear. That's what an exponent, that's what logarithms do. They take something exponential and they make it linear. Okay? So I want you to imagine, okay, that here's my hands on a TV screen. Okay, my fingers are there on either side of the screen. And which is my left hand? This is my left hand? To you, is that left?
That's right, so
This is left. So imagine that this number is 0 and this number is 100. How wide is this screen. It's 100 wide.
Mhm.
Where is 10? 10 is going to be about there, wouldn't it? Now imagine that I take this and I zoom in with the camera until it looks like this. Now what's this?
0.
What's this?
10,
So what's this number here?
1.
1. So zoom in. And now what? Now I have 0 and 1. And what's this number here?
0.1.
0.1. So every time the camera zooms in, I'm expanding this out and I keep zooming in from 0 to 10 or 0 to 100, 0 to 10, 0 to 1, 0 to 0.1, right? Every time I zoom in, I'm doing it a factor of 10. So if this axis is over here is exponential, what I'm saying is, what is this point over there? This would be 0. Does this graph ever able to go to 0? Every time I zoom in, what am I doing? I'm getting closer. I'm getting to 0.01, 0.001, 0.0001. I keep zooming in. Will this line ever go all the way to the left edge? Okay, so how far does this line go? And the answer is, it is infinite. This line goes to infinity. It never goes to 0 because what's the smallest a wavelength can be? Can a wavelength ever be 0?
No.
It can be as small as you want, but I can never be 0. So I have to graph it exponent or logarithmically because it goes on forever. Over here, it goes on forever. So this graph, this curve, and the curve really looks like this. It goes up steeper than it goes up. So it's not a bell curve. It's not a big deal, but it's not a normal distribution. It's not a bell curve. It comes up steeper and then it gradually decreases over here to the right. How far does this line go to the right?
Infinite.
Goes infinitely.
It goes infinitely. How far does it go to the left?
No.
It goes infinitely. So what is the length of this line?
Infinite.
Now, the graph, as I go to longer wavelengths or to shorter wavelengths, logarithmically, will get smaller and smaller. The value gets smaller and smaller. It approaches 0. Can it ever go to 0? Remember, a blackbody can give off wavelengths in all bands. So can it ever be 0? Answer, no. What do you call a graph that gets close to 0 but never comes there? Get off your lazy. What do you think I'm going to say? Get off your lazy what?
Oh, an asymptote.
Get off your lazy asymptote. So this graph is logarithmic and asymptotic.
You're bringing back terrible memories.
Oh, just wait. Today is gonna be a blow your mind day. Because what we're about to do is really fun. But it's gonna blow your mind because you are trying to be rational human beings, and life and science and knowledge and truth is not all rational. But do you understand that this graph is logarithmic, meaning I have to do powers of 10, and it's asymptotic. It goes forever and it never comes into this. Do you agree that there is an area underneath this curve?
Yes.
And then the question I have for you is, how much area?
Would it also be
The
infinite?
infinite.
Okay, so Ryan and Zach are both saying infinite. Do you agree? Aaron, what do you think?
He thinks it means approaches infinite.
Well, if something is approaching infinity, then it is infinite. What do you think, Tim?
I think it goes on forever.
So here is a question for you. What do you call a line that surrounds something? If I said put a line around something, what are you creating?
Boundary.
Close.
Perimeter.
Oops. That's the question I'm asking you. Can an infinite perimeter circumscribe a finite area? I like that word, circumscribe. What does that mean? To write around. Can I have a finite area surrounded by a line that you could never draw?
Finite area?
What's the answer to that question?
Isn't there something like a fractal where it's like infinite perimeter? With
Zach, where did you go to high school?
Naples Central.
You must have had some good teacher somewhere down your line. Where did you learn about fractals, dude?
I honestly kind of learned about it online with watching those like, really trippy videos of people zooming in on
Yeah, I've seen it
fractals.
too.
How many? Okay, well, here, let me do this. I'm going to come back to this, so I'm going to hide for a second. And I'm going to go online, and I want you to see something called. Well, actually, no. I'm going to make you draw this just for fun. So what I want you to do, and I'm going to get rid of this, but I want you to remember this diagram. And I want you to draw an equilateral triangle in a color. Okay, so you're going to draw an equilateral triangle in a color. Do you agree that is an equilateral triangle? Let's say that each side of this equilateral triangle is 1 foot long. What's the perimeter of this equilateral triangle?
3 feet.
3 feet. Okay. Now, what I want you to do, and I'm going to see if you can do this, is for every line segment, break it up into 3 equal parts. Okay, so over here, I'm going to break it up into 3 equal parts. 1, 2, 3. And then over here, same thing. Right? 1, 2, 3. 1, 2, 3. And then in the middle part, I want you to make an equilateral triangle. So watch this. I'm going to go like this. Go here. And I'm going to go like this. And I'm going to go like this. And then I'm going to go like this. And then I'm going to go like this. And each middle segment, I'm going to make an equilateral triangle. And there's my middle segment. And I make an equilateral triangle as best that I can. Maybe it's not perfect. Okay. Now, what's my perimeter? How long are each of these little yellow line segments?
A third of a foot.
Right, 4 inches or a third of a foot. And now I had 3 feet was the perimeter. And now what's the perimeter going to be? For every place there was 1, there's 4/3 bigger. So it's times 4/3. Now it's going to be 4 feet. Okay, so do it again. Every middle segment. And I want you to do this. So you could draw it by hand. I'm doing it on a computer. I don't know if this is better. Takes a long time, doesn't it? You get the idea, right? How big will the perimeter be now? Will it be 4/3 as big? I want you to do that again and again. Etc. Okay, and what I'd like you to do is every time you do it, are you getting the idea that the perimeter is growing by 4/3?
Mm-hmm.
So if I do this once, it's 3 feet times 4/3. If I do it twice, it's 3 feet times 4/3 times 4/3, or 4/3 squared. If I do it 3 times, to the 3rd power, to the 4th power. Now I want you to do it 1,000 more times. Okay, so I want you to do this 1,000 more times, and then you're going to turn that assignment into me. Here's the question. What's this perimeter if I do it 1,000 times? Get out your calculator and do it. What do you get?
I got an overflow error. So,
You got overflow error?
yeah.
The 1.33 to the power. I don't know how to do that on my calculator. To the power of 1,000. Error. Okay, how about instead of doing it 1,000, how about you did it for 500 times? What do you get?
.8 times 10 to the 62nd power.
Times 10 to the 62nd power? 62nd feet? 62nd, how big is that? That's, if I in feet, that's bigger than the universe. You get the idea that's a really big number? How long would it take you to draw that? And that's only 1,000 times.
Billions of years.
Right? You would never be able to do that. You would go crazy, you'd make a mistake, you'd run out of colors. So what you'd have to do is you can't do that. Would you agree that, and that's only 1,000, what if I said do it for 2,000 times? So are you agreeing, like Aaron said, that the perimeter is approaching infinity? But are you also convinced that the area of this thing would never grow outside of those bounds. Right? So what's the area inside of that circle? Isn't that area a finite number? Even though the perimeter is infinitely long, the area inside is finite. Does that make sense to you? Anybody know what this is called? This is called Koch's snowflake. So now I can show you this. Koch's snowflake. Okay. This might be fun. That's what I've been drawing, isn't it? And if you do it long enough, you get these really cool patterns. And you can do neat things with it. So watch this. Here's the length. 3 times 4/3 to the n power. But look at the area. As you go on forever, the area is limited. It doesn't get bigger forever. It gets smaller because each time you draw it, how big are those triangles you're adding? Smaller and smaller. So what I can do here is I can go to video search. And if I go to Koch's snowflake, I can do this. So let's do this video.
Hello friends, I'd like to show you a shape that has some really interesting properties. We can create this special shape by starting with an equilateral triangle, removing the inner third of each side, and then placing another equilateral triangle in the place where the side was removed. If we repeat this process infinitely, we end up with a shape known as a Koch snowflake. And this snowflake is fascinating because although it has a fixed area, it has an infinite perimeter. So how can a shape like this mathematically exist? Well, as the number of generations increases, the area does increase, but less and less each time. At first, the area increases by 1/3 of the original, then 4/27ths, then 16 243rds, then 64 2187ths. You can see how the amount of area added with each successive generation is very quickly trending towards 0. In mathematics, this type of sequence creates what is known as a limit. And what it means in this case is that although it may intuitively seem like the shape's area will grow infinitely, it actually doesn't. There's a limit to the growth. This chart shows how the shape will never grow beyond 1.6 times its original size, which is just a triangle. And because the shape is limited to this 1.6 value, we can say with certainty that the shape has a fixed and non-infinite area. Simply by being able to see this two-dimensional shape in its entirety, we can prove that the area is finite. If the area were infinite, there would be no boundaries to see. And with no boundaries, you really haven't got a two-dimensional shape at all, only a blank infinite plane. The perimeter is a different story. As the number of generations increases, the perimeter of the snowflake continues to grow and grow without approaching the limit. The math works like this. Each generation of the snowflake has a perimeter exactly 4/3 of the previous generation. If you zoom in and look at just one side of the triangle, it becomes easier to understand. With each generation, the perimeter that is added is 4 times 1/3 of the original length, giving a total growth of each generation of 4/3, or 1.3 recurring. Because this number is greater than 1, the perimeter will continue to increase, trending towards infinity. This is the most non-intuitive aspect of the shape, because it seems as if the perimeter could be measured, but it cannot. Because no matter how far we zoom in on the shape, there would always be more perimeter to measure. And that's how you can mathematically have a shape with a fixed area, but an infinite perimeter. Hopefully you learned something today, or simply found this video interesting. Either way, if you'd like to see more videos like this, make sure to subscribe.
What do you think? That's kind of cool, isn't it? I mean, I hope this is a little bit mind-boggling to you that we did this. So when I go back to everything that I did before and I said, you know, look at that question. Can an infinite perimeter circumscribe a finite area? What's the answer?
Yes, it can.
Yes. Okay. Well, as it turns out, when I look at Planck's blackbody distribution, which is this graph, how long does the axis go to the right? This curve go? Infinite. How far does it go to the left? Infinitely small, because I can have a wavelength anywhere that I want. But there is an area underneath this curve. And that area is finite. Finite area. Well, that finite area is the total irradiance. The total amount of energy that a black body emits, E star, which is sigma T to the 4th. In other words, this is called Stefan Boltzmann's law, which says that E star is equal to sigma T to the 4th. T is the absolute temperature of a black body. And that's what Stefan Boltzmann's law is. So right now, do a Google search of Stefan Boltzmann law. And what do you have? What does it say? What do you have, Sam? What did you find, Sam?
It says that it is the total radiant heat power emitted from a surface that is proportional to the 4th power of its absolute temperature.
Okay, so that's exactly what I've written, right? That's exactly where are you at? Are you on Wikipedia or what are you looking for?
That was like from Britannica, I think. So
Okay, I like Wikipedia for a lot of science. I don't like it for anything that has any sort of controversy, but Stefan Boltzmann law, not probably controversial, at least not yet. What do I mean by the absolute temperature?
It's like temperature at a certain location.
No, but what does the word absolute mean? What do you think?
In like exact.
No, not in this case. What's a synonym for absolute temperature? Aaron, do you know?
No? No.
Kelvin temperature. Okay, here's a weird thing. Today's temperature is 5 degrees. Tomorrow's going to be twice as warm. What temperature will it be?
$10.
How did you get that?
5 times 2.
Okay, so if I said it's twice as warm, you're multiplying by 2. Is that what you're telling me? Does everybody agree with this? Okay, today's temperature is -5 degrees Fahrenheit. Tomorrow's temperature is going to be twice as warm. What temperature will it be?
yeah, wouldn't it be 5 degrees?
Okay, so I have somebody saying this. 5. Anybody else say something different?
-10.
I have -10. Okay, does that make sense? I said it's going to be twice as warm and you telling me it's colder. Why did you say 5, Shannon?
I was just going warmer, so
Well, if it was -7 and it was twice as warm tomorrow, what would you say it would have been then, based on your reasoning? Are you saying +7? So it's colder today, but tomorrow when it's twice as warm, it'll be warmer. Then that doesn't make sense. What if I said it's 5 degrees today and it's going to be half as warm tomorrow? What would you say? You guys are insane, right? You guys don't know what's going on. Besides, what did I say? I said it's twice as warm. You said I multiplied by 2. And so when you multiply by 2, you get -10. Why does this not work? If you had a banana and I said double the amount of bananas that you have, how many would you have? 2. Can you have -2 bananas? There's no such thing. There's no such thing as a
Well-
negative banana.
Well, to be fair, if they're taken away from you,
Doesn't matter. You may owe bananas, but there's no such thing as a negative banana. In other words, I need an absolute scale. Absolute scale. An absolute scale, 0 means 0. 0 bananas. Oh, yes, I have no bananas. I have 0 bananas. If I have 2 bananas, how many bananas do I have? 2. 1, 2. Tomorrow I will have twice as many. I will have 4. Easy. Temperatures must work on an absolute scale. So for instance, let me do this. Temperature of the sun is temperature of the earth is 15 degrees Celsius. These are facts you should know. On average, the temperature of the earth is 15 degrees Celsius. The sun is 5,703 degrees. Something like that. Now, watch this. And you need, this is so important. I'm telling you, you better learn this quickly. Okay? When I ask this question, what kind of a question is this? When I said how much warmer is the sun than the earth, what kind of a question is this? This is a what?
Would it be a comparison or difference question?
Oops. It is a comparison. Okay, now watch this, guys. Ready? Ready?
That's a question.
You just said that's a question. That was a Pavlovian response. When water vapor condenses,
Latent heat is released.
latent heat is released. There's a Pavlovian response. Here's a Pavlovian response. When I say comparison, you say the word ratio. Comparison.
Ratio.
When I say the word ratio, you say the word fraction. How much warmer is the sun than the earth? What kind of a question is that?
Comparison.
Comparison.
Ratio.
Ratio.
Fraction.
So in order to answer this, you say it's the temperature of the sun divided by temperature of the earth. Okay? So if that's the case, I go 5,703 degrees Celsius divided by 15 degrees Celsius And the degrees, what is the first thing that happens to the degrees Celsius? They go away. And now 5703 divided by 15, what is the answer?
380.2.
How much?
380.2.
380, 280?
380.
Okay, I'm doing something wrong here, but it doesn't matter. 380. So if I said how much warmer is the sun than the earth, you would give me 380 times warmer. Okay, I tell you what, make everything in the universe 14 degrees colder. What's the temperature of the earth now? What's the temperature of the sun?
5,689.
How much warmer is the earth than the sun?
Same ratio.
No, well, 5689 divided by 1. So you're saying it was 380 times warmer. I cooled things down by 13. Now it's 5,700 times warmer. Let's cool it down by another degree. What's the temperature of the earth? How many times warmer is in the sun than the earth? Divide by 0.
It's impossible.
Infinite. Oh, that doesn't make sense. Make it 1 degree colder. -1. Now how many times hotter is the sun than the earth? -5,700 times warmer? Negative times warmer is colder. Does that make any sense whatsoever? And the problem is, when you do this, you must use an absolute scale. Anytime you have a comparison,
Ratio.
ratio,
Fraction.
anytime you do that, you have to use an absolute scale. Anytime you put it into this equation. So let's go to this. What is an absolute scale? Kelvin. So have we done temperature conversions yet? To go from degrees Celsius to Kelvin,
A long time ago we did.
you add 273. So 15 degrees Celsius is how much?
Mm.
288 kelvins. And it's not degrees Kelvin because a Kelvin is a degree thing. So it's kelvins. The temperature of the sun is actually 5,780 kelvins. So I think this should have been, I think it should have been 5507. I should have put this number in there. I couldn't think it fast enough in my head. That's the number it should be. So how much warmer is the sun than the earth? That's a comparison. Comparison.
That's a question.
No, sorry, I didn't mean to snap. Comparison,
Ratio.
ratio.
Fraction.
So it should be 5,780 kelvins divided by 280 Kelvin. Kelvins go away. And what's 5780 divided by 288?
20.1.
20, right? So how many times hotter is the sun than the earth? And the answer is 20. Would that surprise you? That the sun is only 20 times warmer than the earth?
Not really.
Why do you say that to me? Talk to me.
Because if the Earth was 2 times as hot, I mean, we could probably still live there, but 3 times as hot, probably not.
So 20 is,
The 20 is insanely hot.
but would you agree that 5,780 doesn't seem ridiculously hot? But here's the question. Do you agree that the sun gives off more radiation than the earth? How much more? How much more radiation does the sun give off than the earth? I'm not going to break you up into rooms, but I'm going to let you do this right now. I want all of you to work on that problem. And you can talk to each other. Do you know what question I'm asking you? How much more radiation does the sun give off than the earth? So you may have a group discussion. I will be listening to you.
Should we use that E star equals sigma T to the fourth?
Maybe. Well, that's the absolute temperature of a black body. So would that like also include radiation?
Well, isn't E star the total irradiance? So like how much radiation it gives off?
Yeah, you're right. Yeah.
So like that's what we're solving for when we use that. And we know how much what T is for the sun. So we can just have two equations, I guess.
Yes, we need the. Huh.
So how would you set the problem first? How would you set it up?
Well, it would be a comparison.
It's another comparison.
Okay, what over what?
Yeah, it would be the sun over the earth.
Hold on a second. Would be is that what you're saying?
The amount of radiation from the
The
sun.
radiance of the sun over the earth.
Okay, so you'd have to say right. So this is setting up the problem. What does E star of the sun equal to?
Sigma and then absolute temperature to raise to the fourth.
Temperature of the what?
Sun,
And then in the bottom?
temperature of the earth.
No. This guy, sigma. Did I tell you that's Greek letter sigma? Small sigma. This is a constant to make it work. But what do you see in this fraction? What happens to sigma,
Cancels out.
right? So I don't need to know what sigma is. If anyone's interested. .67 times 10 to the 8th joules per meter squared or whatever. But I don't need to know that because in this problem, it's going away. Now what do I do? And I want you to do it by hand.
So we would have to use Kelvin to make an absolute scale.
Well, would I put it in here? I don't think I need to do that because I want you to do it by hand. And if you want to take 5,780 to the fourth power by hand, go ahead. I don't want to do that. There must be something easier. Lena, what do you see? What can I do here?
Would
Yeah.
you use logarithms?
No, I don't want to use logarithms. Logarithms are never going to be my first choice in anything. I hate logarithms. I'm lazy. I want to do something simple. What can I do here? What do you think, Zach?
I was kind of thinking about the logarithms, and if we if we did, then the log of 4 would cancel on
No, I don't want to do logs. I'm not going to, other than to know that that graph is logarithmic and what that means, I'm not going to ask you about logs. We're not going to use logs.
I'm not 100% sure, but wouldn't the power of 4 just cancel out on both sides? Because
Does the power of 4 cancel out like that? Lena, you're going yes? Oh, wait a second. Hold on. Are you telling me that 3 to the 4th divided by 2 to the 4th is equal to 3 halves? Isn't that 3 times 3 times 3 times 3 divided by 2 times 2 times 2 times 2? Are you telling me that I can just cancel that? That doesn't make sense. Lena, you're not saying I can cancel 3s and 2s.
Yeah, no. Mm-mm.
Can't I do this though? Please excuse my dear Aunt Sally. Three halves times 3 halves times 3 halves times 3 halves. Isn't that going to be just 3 halves to the 4th power? So couldn't I just do this? But what's this? What's that in the circle?
20.
Right? Isn't that in the circle the question? How much warmer is the sun than the earth? And where do you know the answer to that?
20.
Well, isn't 20 to the 4th 2 to the 4th times 10 to the 4th?
16,000.
16 times 10 to the 4th, or 1.6 times 10 to the 5th, or you could say that's 160,000. And you'll get better when you do your worksheet on your lab, because we're going to be dealing with exponents. So it'll give you a chance to review them. So how much more does the sun radiate than the earth? The answer is 160,000 times more. But wait a second. Is it giving off 160,000 times more energy? Shannon, what do you think to that question?
No,
What am I missing in this? What's wrong with that?
wouldn't it be like 160,000 times the amount of radiation? Or
Finish. You're missing one thing right after that. It's giving off 160,000 times more radiation. What am I missing? Lena?
Are you missing your unit?
Well, what? Yeah, but what is the unit of irradiance? Aaron, do you understand what's going on here?
No.
What are you getting confused over?
Exponents? The exponents.
Okay, Aaron, here, let's do this for a second. Well, while you guys are figuring this out, Aaron, Do you understand what I've done here?
Yes.
Okay. And then do you understand that I can take the exponent out? And then I'm just taking the ratio, which is the question, how much hotter is the sun than the earth? We just figured that out, right? We knew the answer is 20. So 20 to the fourth, if I do that, and I'll let you figure this out, that's 160,000, 20 to the fourth, 20 times 20 times 20 times 20. But you know that, right? So the answer to this question is 160,000. This question is, how much more is the irradiance of the sun than the earth? Tim, this is what you said. I'm combining those two things. But what is irradiance? Is it the amount of radiation a black body gives off?
Yeah.
You're missing something.
Well, isn't it over a distance too? Because it's watts per meter squared.
It's not over a distance, it's over an area, per area, right? So per area. So if I had little carpet tile, 1 meter by 1 meter long, radiation that's coming through it from the sun is 160,000 times more energy than the radiation coming from the earth. So it's 20 times warmer, but it's giving off 160,000 times more energy. Do you agree that's a bigger number? But what do you know about the sun compared to the earth? How many carpet tiles are going to be on the sun compared to the earth?
A lot more.
A lot.
How much bigger is the sun than the earth? In fact, what am I asking for? What bigness measure am I looking for?
Surface area.
So I want the surface area of the sun divided by the surface area of the earth. What's the formula for surface area? Do you know? You can do a web search on this.
Uh, 4 pi r squared.
4 pi radius of the sun squared divided by 4 pi radius of the earth squared. Let's simplify. 4 pi goes away. Can I cut out the square? No. I can do this though. Do I know how much bigger, do I know these values?
They're out there, yeah.
They're out there. Where's the easiest place to find them?
The internet.
Well, I was thinking page 2 of the notes because I gave you this. So if you go to page 2 of the notes, where are my notes? There we go. There. The radius of the sun is 870,000 miles or 1.4 million kilometers compared to that of the earth, which is 6,400 kilometers. So what I could have done is doesn't matter which unit I use, 1,400,000, that's 1.4 million divided by 6,400 squared. Okay, so the first thing, 2 zeros go away. So what is this number? What's 1.4 million divided by 6,400? $218.75. But I have to square it. So I get 47,851. So the sun has a surface area 407 or 47,851 times bigger than the Earth. Times it's giving off 160,000 times more energy. Which means the sun is giving off 7.6 times 10 to the 9th times more energy. 7.6 billion times more energy is coming from the sun than the Earth, because the sun is 20 times hotter and way bigger. Do you understand, in the grand scheme of the solar system, who's giving whom what? The sun gives us energy. Or it's giving off way more energy. 7.6 billion times more energy. And that makes more sense, doesn't it? Why is the sun giving off energy? Let me see how you're going to answer this question.
Is it like stars are like elements on the inside that are burning, and like the space is trying to contract it, and so it's creating more pressure, creating higher elements, which makes it burn more. And
Okay, well, all right, so let's Zach, let's make life real simple, okay? Why is the sun giving off energy? Because it's what?
It's burning.
No, well, before that even. It's hot, right? Why is the sun giving off energy? Because it's hot. The hotter it is, do you agree that hotter objects give off more energy than colder objects? It's proportional to the temperature to the 4th power.
Mm-hmm.
Okay, now why is the sun hot? Zach said because it's burning. Can we be more scientific than that? Well, how, Sam? You're talking and it's muted, so we're just seeing your lips moving.
Thank you. I was wondering, how did you know I was talking? Because it's burning hydrogen.
Mm-hmm.
And what do you call that process? What's the process of burning hydrogen? Because in order to burn hydrogen, you need oxygen, right? We don't have any oxygen on the sun. It's doing more than just burning. It's not on fire. It's not like somebody took this big ball of hydrogen and lit it with a match.
Well, it's burning hydrogen and it's turning it into helium. So
okay, hydrogen turning into helium is called what process?
Aaron says fusion.
It is fusion, as opposed to nuclear power, which is what kind of nuclear power do we do?
Fission.
We have fission. Fission is great.
Fusion is going to be much more efficient.
Fusion is great. The only problem is, can we do fusion? Yes. We get energy from fusion. The problem is it takes more energy to get the fusion going than we get back from it. So we have to make things so hot to get fusion. We use more energy than we get it back. The sun is
just
somehow
needs a kickstart, and then we'll.
If we could just figure that out, right? So if you look over here on this page, hold on, resume share. It says, the sun is like a nuclear reactor. Helium fuses into helium, known as fusion. We have energy being converted to, or mass converted to energy.
Wouldn't that create plasma though?
Well, yeah, it does. So E equals mc squared, mass times the speed of light, which you'll see in the lab. And the speed of light is 186,000 meters or miles per second, or 3 times 10 to the 8th meters per second. You'll see those numbers later, so don't worry about them now. But that's a big number. And then we have mass converted into this. So hydrogen becomes helium. And in doing that fusion, it destroys mass. Mass destroyed creates energy. It is so dense. There is so much mass. We only have about 100 billion years left before the sun will burn itself out. So we're limited. Don't make plans for the future. So that's what's going on. We are destroying mass to create energy according to Einstein's equation, E equals mc squared. And because it's burning hydrogen, so quote unquote fusion, we are getting energy. Energy is being radiated from the sun. Radiation is a way of getting rid of that energy going through space. Now, Sam, you said, doesn't that create plasma? And the answer is yes, but sometimes the sun ejects plasma. That's called a flare. When that flare goes through space, that plasma travels through space, and then it hits the Earth's magnetic poles, goes around the North Pole and the South Pole, and that plasma interacting with our magnetic and the ionosphere creates what? What are those called?
Northern Lights.
The northern lights, the aurora borealis or the aurora australis. So we are actually getting plasma, the solar wind, intersecting with the Earth, and that's what the northern lights are. If we have a big flare, sometimes that interferes with the Earth's system. If we have a big enough solar flare, we can actually get power outages on the grid. The power outages on the grid is like an EMP. What's EMP stand for?
Electromagnetic pulse.
An electromagnetic pulse. When we set up a nuclear bomb, we get an EMP. If we detonate an EMP above the Earth, big enough, we can knock out all electrical circuits. We can totally take down the United States power grid. If you look at the people who are caring, if somebody detonated EMPs above the Earth, above the United States, they would mess us up badly. You guys have watched enough movies. There's actually a big task force on the planet that cares about this. It's dangerous.
But didn't when they detonated the first or second atomic bomb, didn't it make a little bit of plasma?
Yeah, and an atomic bomb makes an EMP. The problem is you're probably blowing up everything that's running anyway, so it doesn't really matter, you're burning it. But if you set it up above the Earth, you could knock out everything, turn off everything, ruin it, destroy our electrical grid, and not destroy anything. We would just be without power.
Mhm.
And have you thought about what the United States would be like without power for a week? That would be bad. So this is a big thing. Anyway, it's all related, right? This is all related to what's going on. But the sun is giving off energy. Is giving off an energy at 160,000 times the rate of the Earth, based on its temperature being 20 times warmer, based on the fact that it's way bigger, gives off radiation. That radiation then does what? What can you tell me the radiation that comes from the sun, what is it doing?
Is it like that one diagram we drew?
Yeah. I mean, what would you say though? It's doing what?
Emitting. One sec.
Do you agree that it emits radiation? How? What's the word, Nina?
Isotropically.
Right? And you can imagine the radiation as being a really large shell of radiation that expands out. And what happens when radiation, like if I took a flashlight and I shone it in your eyes, so imagine this, I'm showing, right? Do you agree that's really bright? What's going to happen to that radiation the further away I go?
Does it disperse?
It disperses, it spreads out, right? It becomes less intense. So the further I go from the sun, the less intense the radiation. So I want you to imagine that this shell of radiation that comes from the sun, imagine that you're watching the Death Star explode on Star Wars. and you see this big expanding sphere. That sphere will eventually intersect the Earth, which is a really small sphere, really far away. How far away is the sun and the Earth? On average, it says it on page 2.
93 million miles.
93 million miles away. So that ball of radiation is a sphere with a radius of 93 million miles. And we're only intercepting a little bit of that radiation. So you can imagine that what I have is a sphere of radiation that's so big, it's 93 million miles, and the Earth is intercepting just a little bit of it. It's intercepting 1/2 billion
Wow.
of the sun's total energy. So of all the energy the sun is giving off, the Earth is only getting 1/2 billionth of that radiation.
What does Mercury get?
Mercury's a lot closer, but it's a lot smaller. So I'm not sure what the exact number is, but it's not very big. Venus, not very big. Jupiter, which is really big, is really far away, not very much. So most of the sun's energy is doing what?
Dispersing into space.
Through all this space. So you can be anywhere in the universe, and if you can see the sun, you would see the sun because you'll pick up that light. You'll pick up that radiation. And right now, what kind of radiation do we pick up from stars? When at night, what do we see?
Visible
We see
light.
the part that's visible. I can set up big dishes. These are called radio telescopes. And so I'm looking at radio waves, and I can detect things from far away. We're going to talk about this on Wednesday or on Thursday. SETI. Has anybody ever heard this term? Erin, do you know what SETI stands for? I take it. She seems like she knows what that is.
Yeah, she does. She's spelling it. Search.
Okay, you got the first word right, Erin. I'm going to assume you know what this is. SETI stands for the Search for Extraterrestrial Intelligence. We are going to search the universe for extraterrestrial, outside of the Earth, intelligence. And there's a reason for this. And we're going to talk about this when we get to the next law of radiation. And that's called the Wien displacement law. So we're going to actually deal with this. But radiation's going all out, and the Earth is only receiving a little bit of it. So now I want you to imagine this sphere of radiation that's 93 million miles is really a big circle, and there's this little Earth. But now I'm going to zoom in on the Earth, okay? So, hey, hold on just a second. Hold on a sec, guys.
So aliens on Thursday?
Yeah. Do you guys believe in aliens?
I don't know.
That'd be so funny if you like just start talking about it.
Aaron does.
I think it's definitely a
I
possibility.
mean, the universe is so expansive. It's expanding as we speak. And I would find it hard to believe that somewhere out there, that there isn't life somewhere else out there.
Well, I thought like NASA like found like an Earth 2.0 somewhere, so I don't know.
Yeah, I know there's a couple planets that like have the capability like Earth to produce life or something.
I would just find it hard to believe that there isn't any other life out there with how big the universe is.
Just us, Sam.
Sorry, guys. It's kind of a sad story. I have a next door neighbor, a couple doors down, and she hasn't done anything for several weeks. And the paramedics are here in the fire department, so I don't know if she's alive or if she needs to be taken to the hospital. So, anyway, so what were we talking about? Oh, I said, here's the Earth. So remember that Earth was a really small circle compared to this huge sphere. Well, what's the sphere going to look like if the Earth is this big? That circle is so big that it's hitting the Earth, that the radiation is going to come in here, and it's going to look like this. The radiation coming from the sun will appear to be all coming from the same direction. Okay, does that make sense? You have to think of this yellow line as this 93 million mile circle. But the Earth is intercepting such a small amount, it's like a big line. You don't know it's curved, it's such a big circle. So what we say about this is that the radiation is what we call parallel beam radiation. Right? So that the radiation is all coming down at the Earth like this. So do you agree that this part of the Earth will be lit? That's all bright. And what's this part of the Earth? All dark. So how much of the Earth is lit? And the answer is half, right? Half should be lit. So this thing is what we call the circle of illumination. That we're lighting half of the Earth. The circle of illumination is what we call a great circle. A great circle bisects a sphere. Do you know what the word bisects means? Cuts it in half. So a great circle is any circle that cuts the Earth in half. And this circle of illumination is a great circle. Half the Earth is lit, half the Earth is dark. Okay? And that's because parallel beam radiation. And parallel beam radiation means that the sun's radiation is coming to us here because it's so far away. By the time it gets here, all the radiation is coming from the same direction. In other words, if everybody on the planet was looking at the sun and they all went, there's the sun, and they pointed toward it, they would all be pointing toward the same direction. Everybody would be pointing in the same direction. Okay? Does that make sense?
I have a question.
Yeah.
We said the Earth is a black body too, right?
Yes.
Does that mean we do the same thing with like the moon? And
Yeah. But here's the thing about the Earth's black body. We know that that a black body, by definition, has an albedo of 0. What's the Earth's albedo?
Not 0 because clouds reflect.
Yeah, and we knew, you should know the number, right?
30%, right?
30%. So 30% is reflected. So it's not a black body, it's actually what we call a gray body, if we want to be technical. So we're not really looking at it as being always absorbing, but we are talking about the way it gives off radiation. And that's what we're going to need to discuss on Thursday. So does that make sense to you? So right now we've done Planck's black body radiation, which is a distribution talking about the wavelength and the amount of radiation that's coming out. We have really talked about how the wavelength varies, but we've said that the area underneath the curve represents the rate of radiation being emitted per meter squared. And that's determined by Stefan Boltzmann law. The next law is Wien's displacement law, which we will talk about on Thursday. But between now and Thursday, you need to finish the lab. Okay? So you need to work on that lab, turn it in, but I will let you turn it in again for a better grade. I just want to see what you can do independently. And I want to see if you can follow the directions. So read it carefully. So does everybody make sense? That's what's doing on. You've got outline or the worksheets that are due on Monday next week. So if you're not done with it, that's fine. But this will all be put together in some more detail. How do you give me a finger today, 1 to 5? How well you understood today's lectures? Okay, I've got some 3s. I've got a couple 4s, 5s. Okay, Isaac, can you give me an idea of why what gave you a 3? What's confusing you?
I think I just need to look over it a few more times.
Was there anything specific?
I think just the numbers. I'm not a big math person, so.
Okay, well, rewrite the notes, Isaac, and tell me what the numbers are in conclusion. But the thing that you want to keep in mind is that comparison ratio fraction idea. When you see a fraction, that means there's a question in there. How much bigger is the top than the bottom? And if we need to review that, we'll start with that on Thursday, okay?
Okay.
But I think that's good right now. I think we're good to go. You guys did fine today. This is heady. This is a little bit more mathematical, a little bit more math and physics. So hopefully it makes sense to you, but did the basic idea of the fractal and stuff. And I am going to blow your mind because we are going to talk about SETI and we're going to search for intelligent life in the universe and why we can try to figure that out. And we'll talk about the origins of life and that kind of stuff. So it'll be a fun discussion on Thursday. Okay?
Did you say do the math lab by Thursday?
Correct.
Okay.
And turn it in. And then I want to see what you do independently. But I will not count you off if you're bad on everything. Okay? All right, guys. We'll see you on Thursday. Have a nice day.
Thank you.
Have a good day.
Bye.